You know, it isn't lost on me that these videos have a very particular structure, and that given how it all turns out, it might look like there's a level of affectation involved. And let's just be honest, when you do a project kind of like the one that I'm doing at the moment, some level of affectation is guaranteed to kick in. But there's a broader thing working there too. This is actually my 50th video, which is kind of strange, and we're also at the halfway point through the semester. That seems like a good chance to stop and reflect. And one of the things that I've benefited from over the last 49 videos is the fact that I get a chance to edit for a week, and I learn a lot during that process. And it gives me a chance to do something really important, which is every time that I find something that I accidentally do well, then I just do it again. Every time that some weird little mutation happens in these videos, it's just a chance to repeat it and act like I planned on it the entire time. So the blocks, the transitions, the provocative thought, even this cold intro, these things were all sort of happy accidents that kicked in along the way. And there was a very important person in my life that helped me to internalize the fact that if you do something right, then you ought to do it the same way every time. And one thing that I did well the first time that I made any lecture videos, which would have been about 15 videos into my little stupid YouTube career, one thing that I did okay was I stopped and reflected halfway through. This was when coronavirus was at the height of its impact on the university. And I stopped and reflected because I was already exhausted. And I thought about one of my best teachers when I was growing up. Her name was Sister Rosalinda. She was my math teacher in middle school. And she was awesome. She was totally awesome. She was a great teacher. She was fun to hang around. She had a warm sense of humor. She didn't tolerate a whole lot of crap when we were doing math. And stopping and reflecting is a good thing anytime, but I think it's really useful halfway through a semester when you're working as hard as you are, because your hard work is one thing that has brought you to where you are. Other factors have been at play too. Let's just be honest. Luck has played some role in all of this. But so too have those people that have cared the most about you and provided the most support for you along the way. That might involve your family. That might involve teachers like Sister Rosalinda did for me. It might involve television personalities that influenced you more than you realized at the time. And whenever something like this happens, whenever you have a chance to stop and reflect, I think it's useful not just to think about how hard you're working, but about all of the people that will be super proud to know how hard you are working, given how much they've invested in you in the past. And one other thing that I did right one time was steal a play out of some important person's playbook by encouraging students, and for myself, to just take 10 seconds of silence, to stop and think about those people that have worked the hardest and invested the most in you, and therefore would be the proudest to know how hard you're working. 10 seconds of silence. I'll watch the time. Whoever it is that you just thought about, it probably means a lot to them that you thought about them just now. And for some of us, there isn't a chance to give them a call because they've since left us. But if you have the chance, maybe take the time and let them know that you just thought about them. Hey everybody, welcome to PS 231. So we find ourselves right at the core of our class in game theory. So the first few weeks are the raw foundations. What do you need to know in order to be able to fully appreciate what's going on in a game? And what we'll be talking about next week and after will be how do we take the games that we've been talking about lately and make them a little bit more elaborate to incorporate more interesting features, whether they're theoretical features or real world features. But right now, we're talking about what's a game and how do you study it. This is the core, right? This is why it's a good time to stop and reflect. Last week, we talked about Nash equilibrium, which is the most standard way to study a game. How do we take a fable and take it to its ending? Nash equilibrium is the mechanism of that. And throughout last week's lecture, I just kept saying pure strategy Nash equilibrium, and I never really talked about what I meant by pure strategies, which is just some shitty teaching on my part, per usual. You'll see why I was saying pure strategy Nash equilibrium today when we talk about Nash equilibrium in general. We were talking about just one sliver of Nash equilibrium, and it turns out that I need to show you something else in order to deliver the entire punchline of what is Nash equilibrium. And today's lecture is going to focus on what we call mixed strategies and mixed strategy Nash equilibrium, or just Nash equilibrium. So in the previous lecture, focused on pure strategies, you could only do one thing, right? You always drove on the left side of the road, or you always drove on the right side of the road. You always went straight, or you always swerved. You always had one platform, or you always had another. But that doesn't seem to be what happens out in the real world. A lot of the time, people are making choices where it isn't obvious what they're doing every time, because if it was obvious, then other players would be able to create bad outcomes for them. In particular, we'll be spending some time talking about baseball again today, and go back to Uncertainty Week, go back to the provocative thought where we talked about baseball, where I said that one source of uncertainty in life is strategic randomization, the fact that there's somebody out there that wants to keep you guessing. So these randomized strategies, the fact that you mix it up, the fact that you don't throw the same pitch every time, the fact that you might not always go straight or swerve all the time, the fact that when you play rock, paper, scissors, you don't always put out rock, you don't always put out paper, you don't always put out scissors. Certain kinds of games really introduce this rich notion of strategic randomization, which we'll see can also enhance our understanding of some of the games we talked about previously. So if nothing else, I'm looking forward to showing you all this because of that, but I think you're going to learn some interesting political lessons along the way. So get yourself some tea, get yourself some soft pants, get yourself some aromatherapy, get yourself some binaural beats, get yourself whatever it takes to get yourself really locked in, and we'll get to it. In the A block, I just want to show you what randomized strategies look like. I want to talk about what is a mixed strategy. So now we're going to enhance what a strategy is by allowing each player to choose a lottery over their available actions. If I can drive on the left side of the road or the right side of the road, maybe I don't have to do the same thing all the time. Maybe I drive on the left side of the road a quarter of the time and on the right side of the road 3/4 of the time. We'll see that this introduces a notion of expected utility, and we'll see that we need to add those two von Neumann and Morgenstern assumptions, work with expected utility, and that will allow us to determine how the players evaluate their own choices when they're faced with players who are randomizing against them. Then in the B block, we'll talk about how to use this approach to study a game of anti-coordination. We'll talk about baseball. And we'll see that in the baseball game, pure strategy Nash equilibrium wouldn't have been enough to get us where we need to go. You saw that on your problem set last week. We saw that pure strategy Nash equilibrium doesn't necessarily get you where you need to go in every game, and anti-coordination, matching pennies or baseball, is the clearest way to see that. We'll see that we can take matching pennies or baseball or whatever you want to call it and study it in a perfectly reasonable way that allows us to make a prediction, although it's a prediction that's a little bit harder to observe because we might only observe one choice when the players were indeed randomizing underneath the hood. Then the C block, I just want to get some extra practice by studying Chicken, one of my very favorite games, and we'll see that Chicken introduces the chance for us to do a little bit more interesting welfare analysis when we compare its pure and mixed strategy equilibria. In particular, I just want to show you that a game that has pure strategy Nash equilibria can also admit mixed strategy Nash equilibria, and what is more, those mixed strategy Nash equilibria might offer qualitatively different substantive interpretations than the pure strategy Nash equilibria. Which is to say, if you thought that you knew everything about Chicken just based on what we did last week, there's more Chicken than you ever thought about. So that's what we have to look forward to. Like I said, this is a tough lecture. You're going to do great, but you're also going to struggle a little bit. Struggling is part of doing great. Struggling well is part of doing great, and you've been doing a great job of it so far from everything I've seen. So just keep going. This is going to be a tough one, but this is also one of the main punchlines of a class like this one. So I really can't wait to show it to you, even though it might be a little bit hard for you along the way. But once you see it, you're going to say, oh yeah, that's the good stuff. So let's get started. So here in the A block, I just want to introduce the notion of a mixed strategy. Don't even act like those harps and angels don't get you excited. You're totally excited about that. Totally excited. So excited. So, like I said in the intro, the big idea here is that it might not be the case that a player wants to play the same strategy every time, right? It might be the case that you want to mix it up. And we don't have an encoding for that so far. All that I set up to this point is the players choose some action, little a, out of their action set, capital A. They might always drive on the left, they might always drive on the right. They might always go straight, they might always swerve. They might always stay silent, they might always tattle. I don't know why I have to do this whenever I do this, but there's something kind of addictive about doing things like this. Ow! So what we need to think up here is a method for encoding the idea of mixing it up. And in order to show you what something like that looks like, let's just come up with a game to study in the present moment. Let's just study the Stag Hunt. So you'll remember that the Stag Hunt is a game between two players who can cooperate with one another by doing something ambitious that requires both of their attention, or they can peel off and do something less ambitious that they can do by themselves. So in particular, I'm a hunter, you're a hunter, we are two hunters. And I can go hunting for stag or I can go hunting for hare. And you can go hunting for stag or you can go hunting for hare. Okay? And the idea is we both need to go for the stag. In order for us to get a stag, we both have to go for it. And if one of us goes for a stag and the other one doesn't, then the one that went for a stag goes home empty-handed. And they have to eat, like, pasta sauce. However, you can get a hare by yourself if you want to, which gives you 1 happiness point in comparison to the 2 happiness points that you get if you both get a stag together. If I go stag and you go stag, that's 2 happiness points for me and 2 happiness points for you. If I go stag and you go hare, then 0 happiness points for me. I'm eating pasta, although it's pretty good, right? And 1 happiness point for you. You're eating rabbit stew. If I go hunting for hare and you go hunting for stag, then 1 happiness point for me, rabbit stew, 0 happiness points for you, ravioli with pasta sauce. And then if we both go for a hare, 1 happiness point apiece. So if you were so inclined, you could do a Nash equilibrium analysis of this game in pure strategies the same way that you have it at this point. It could be steady state, it could be best response. Either way, you would learn that this game has 2 pure strategy Nash equilibria. I'll leave that to you to find. That's left to the reader as an exercise. What I want to focus on here is the idea that I might not go hunting for the same thing every time, and you might not go hunting for the same thing every time. Up to this point, a strategy has been choose some little a sub I and your big A sub I, right? So my A sub I up to this point could have been stag or it could have been hare. And that's very restrictive because I might need to mix it up. So what I'm going to do is I'm going to introduce the notion of a mixed strategy. So let me do this in particular first, and then I'll show you a more general definition. And you're like, oh yes, I need general, otherwise I'm not going to learn anything here. Yes, examples are stupid, fat man. Okay, so suppose that instead of I choose stag or I choose hare, suppose that I said, I will go hunting for stag with probability P. Probability P. And because I've only got these 2 actions, if I say that I'm hunting for stag with probability P, that means that I'm hunting for hare with probability 1 minus P. I'm choosing a lottery over my actions. And therefore, it has to be a bunch of non-negative numbers that sum to 1, right? So once I know that I'm hunting for stag with probability P, that implies that I'm hunting for hare with probability 1 minus P. Notice that P can fall anywhere between 0 and 1 inclusive. If P is 1/2, that means that I'm hunting for stag half of the time, and therefore hunting for hare half of the time. If P equals 3/4, then I'm hunting for stag 3/4 of the time and hunting for hare 1/4 of the time. 1/8, 7/8, and so on. But when I say inclusive, what that means is, if I set P equals 1, that means I'm hunting for stag all of the time and never hunting for hare, which is just what I used to call A sub I equals stag. Now it's like a degenerate lottery. I've put a 1 on one of these outcomes in the lottery that I'm choosing with my randomized strategy, with my mixed strategy, which is to say, a pure strategy, like we've studied up to this point, is just a special kind of mixed strategy where we're assigning probability 1 to one of the choices. Just as another example of that, if I set P equal to 0, then that means I'm never hunting for stag and I'm always hunting for hare. That's a pure strategy on hare. So I can go pure stag, P equals 1. I can go pure hare, P equals 0, or anywhere in between, some mix of stag and hare. That's a mixed strategy. It's a lottery over my available actions. The same goes for you. There's nothing that says that I'm the only one that's allowed to mix it up. It could be that maybe you go hunting for stag with probability Q, right? So Q is some number that falls between 0 and 1 inclusive, which is to say, if Q equals 1/2, then you go hunting for stag half of the time and go hunting for hare half of the time. If Q equals 1/8, then that means you're going for stag an eighth of the time and going for hare 7/8 of the time. Same as with me. So P is my mixing probability, Q is yours. If Q equals 1, you're always going for stag. If Q equals 0, you're always going for hare, right? So remember, pure strategies are a special kind of mixed strategy. This is our general apparatus for studying games like this. What we did up to this point is just a sliver. So what that means is I'm choosing a lottery over my actions, and you're choosing a lottery over your actions. Right? It's kind of cool when you think about it, but that's what it means to mix things up. It means you don't always do the same thing. That's why you have to do this dance. Another remarkable thing about this is the following. If you randomize, if you have Q and 1 minus Q, if you have Q and 1 minus Q, that takes my pure strategies and it makes them lotteries. It makes them lottery tickets. Because now I don't know. If I go hunting for stag, I don't know for sure what the outcome is going to be. Back when you were playing pure strategies, if I played stag and I knew you were playing stag, I get 2. If I play stag and I know you're playing hare, I get 0. But if you're not playing a pure strategy, I've got a new set of possible outcomes to think about. And I have to think about a probabilistic mix over those things. So in other words, if I go hunting for stag, there is no longer a guaranteed utility. There's an expected utility. And if I go hunting for hare, there is no longer one utility to expect. There's an expected utility that depends on your mixing probability. Remember, a lottery is both a set of probabilities and a set of numbers for expected utility purposes, a set of utility numbers for each of those possible outcomes. So just for example, my expected utility now of hunting for stag, on the understanding that you're playing stag with probability Q, with probability Q, I'm in this cell and I get 2 happiness points. So it's 2 times Q. And then with probability 1 minus Q, we're in this cell where I'm getting 0 happiness points. So it's 2Q plus 0 times 1 minus Q, which is just 2Q. Notice that if Q equals 1, so that you're hunting for stag all the time, my expected utility would be 2 times 1 equals 2, which is exactly what I get in this cell. Similarly, if your mixing probability was 0, if you were hunting for stag none of the time and hunting for hare all of the time, if you're playing a pure strategy on hare, then my expected utility for hunting for stag is 2 times your mixing probability of 0, which is 0, which is exactly my utility for stag hare. However, if you're going for stag half of the time and going for hare half of the time, then my expected utility for hunting for stag is 2 times 1/2 plus 0 times 1/2 equals 1. So now I've got this richer possibility for stag because now I can think through all of the possible versions of your randomization. If I know your mixing probability, I can use that to inform the expected utility of hunting for stag. Likewise for hare. If I'm going hunting for hare, a pure strategy on hare, and I know that you're hunting for stag with probability Q, then what that means is with probability Q, we're in this cell. With probability Q, we're at hare stag, and I get 1 happiness point. So Q times 1. And with probability 1 minus Q, we're in this cell, hare hare, and I get 1 happiness point. So now it's Q times 1 plus 1 minus Q times 1, which is just 1. Notice that if no matter what I do, I get 1 happiness point down here. I get 1 happiness point for going for hare. Hare is a short thing, you get 1 happiness point. It doesn't really matter what the other person does at that point in time, because you can get a hare by yourself. Who needs strategy? Well, with the Q's and the P's, we kind of do. And apparently this is just going to happen. 8-bit bad guy is just the word of the day. Just for practice, let's go through your expected utilities in response to my mixing probability P. So let's suppose right now that I'm hunting for stag with probability P and therefore hunting for hare with probability 1 minus P. could be 1, 0, could be 0, 1, could be 3/4, 1/4, could be 1/8, 7/8, could be any number you could think about between 0 and 1 right here, and 1 minus that number down here, okay? What's your expected utility for hunting for stag? Well, with probability P, we're in this cell. With probability P, we're at stag, stag, and you get 2 happiness points. And with probability 1 minus P, we're at hare stag, and you get 0 happiness points. So it's 2 times P plus 0 times 1 minus P, which is just 2P. So your expected utility, if you played stag all the time, is 2P. Notice that if P is 1, you get 2 happiness points because we're at stag, stag for sure. If P is 0, you get 0 happiness points because we're at hare stag for sure. If P equals 3/4, then you get 2 times 3/4, which is 1.5. My mixing probability informs your expected utility for going for stag. Just like it was the case with me, your expected utility for going for hare, no matter what my mixing probability is 1. Why? Well, with probability P, we're at stag hare, and you get 1 happiness point. And with probability 1 minus P, I've played hare, and we're at hare, hare, and you get 1 happiness point. P times 1 plus 1 minus P times 1 is 1. Notice also that we can think about just one gigantic expected utility for the whole game. So if I'm choosing my P independent of your Q, and you're choosing your Q independent of my P, which is what's happening here, if I increase P, that doesn't necessarily increase your Q. You can choose any Q you want to. It's not like I'm changing your Q with my P. It's not a sentence I was planning on saying today. What that means is the probability of each of these 4 outcomes depends on my P and your Q in a very simple way. If I'm going for stag with probability P, and you're going for stag with probability Q, then the probability that we find ourselves at stag, stag is P times Q. Notice that if P is 1 and Q is 1, then that means that the probability of being at stag, stag is 1. If either of them is 0, that means the probability is 0. So the probability that we find ourselves at the stag, stag outcome, so that I get 2 happiness points and you get 2 happiness points, is P times Q. The probability that we find ourselves at stag hare is my P times your 1 minus Q. The probability that we find ourselves at hare stag is my 1 minus P times your Q. And the probability that we find ourselves at hare, hare is my 1 minus P times your 1 minus Q. As an exercise, you should just make sure that those things all add up to 1. I just introduced an omnibus lottery that covers all 4 game theoretic outcomes. All 4 elements of the Cartesian product. That has to sum to 1 because it's a lottery. It's a compound lottery. It's my P times your Q. So that's it. That's what a mixed strategy is, in broad brushstrokes, is just a set of probabilities over each of the outcomes. All right? Let me just give you a slightly more rigorous definition of a mixed strategy, just so that I can sleep at night, even though you're not going to get much out of this probably, and I'm sorry about this, but I just wanted to be able to sleep at night. Suppose that I've got a game, which is a set of players, capital N, a set of actions available to each player, capital A sub I, and a utility function for every player, little u sub I, which is my utility for each of the possible outcomes. 2, 0, 1, 1. So what a mixed strategy is, you can think about it a few ways. One way to think about it is it's just a lottery. It's a vector of probabilities over A sub I. So when I choose a P and a 1 minus P, what I'm saying is I will go for stag with probability P and go for hare with probability 1 minus P. And therefore, you can think about that as an element of the set of all lotteries over A sub I. So we talked about that way back in week 3 or 4, the set of all lotteries. I think that was week 4. And so this is no different from that. Another way to think about mixed strategies that I think is a little bit easier for some of the notation for an equilibrium is to think about a mixed strategy as a function, right? A mixed strategy is a function. I'll call it sigma sub I. Sigma sub I is a function that reads in A sub I, it reads in the things I can do, and it spits out a probability. So in other words, sigma I of AI is the probability that I assign to action A sub I under the strategy sigma sub I. In the previous example, sigma sub I, sigma sub 1, we'll say, sigma sub 1, hunter 1, sigma sub 1 of stag is P. And sigma sub 1 of hare is 1 minus P. So these sigmas are just a way to say it's the probability that we find ourselves at a given strategy. It's the probability that we play a given strategy. So it reads in a strategy and it spits out the probability of playing that strategy. All right? And you'll see that this is just an easier way to talk about equilibrium. Finally, we'll say that a mixed strategy profile is just a sigma for every player. It's a set of probabilities for every player. So it's my set of probabilities and your set of probabilities. Therefore, I can write out the expected utility of playing a given strategy, depending on your strategy or everybody else's strategies. All I have to do then is multiply things by the respective probabilities. So the probability of finding ourselves at stag is sigma 1 of stag times sigma 2 of stag. The probability of finding ourselves at stag hare is sigma 1 of stag times sigma 2 of hare, and so on. And this allows me to find expected utilities as need be. In particular, I can write the expected utility of playing sigma sub I against sigma sub minus I, which is just the utility I get from my mixed strategy, calling attention to my mixed strategy against everybody else's mixed strategy. Sigma sub minus I is just everybody else's mixed strategy. Sigma sub I is my mixed strategy. So you'll see what I mean by this here in just a second, but it's more straightforward than the notation would tell you. If I say the expected utility of playing sigma sub I against sigma sub minus I, that's really just going back to the stag hunt and saying, what is the probability of each of the possible outcomes of this Cartesian product, stag hare, hare stag, hare hare. Find the probability of each of those, which is just a bunch of probabilities being multiplied together, PQ, P1 minus Q, 1 minus PQ, 1 minus P1 minus Q, and then multiply that by the respective utility. And that's my expected utility of playing P against your Q. So that's a lot, but that's what a mixed strategy is. And it's now time for us to try to use this a meaningful way. We'll talk about baseball over in the B block. Looking forward to that. So here in the B block, I want to talk about mixed strategy Nash equilibria. And I want to do this by way of example. Let's talk about baseball. So you remember in our game of anti-coordination, I'm a baseball player, you're a baseball player, we are two baseball players, but I'm a pitcher and you're a hitter. I'm throwing a ball that I don't want you to hit, and you're trying to figure out what I'm going to throw so that you can be ready for it. So in particular, I can throw a fastball or I can throw a curveball. And you can be waiting for a fastball or you can be waiting for a curveball. I'm throwing fastball or curveball, you're anticipating fastball or curveball because that sets you up for more success. So if I throw a fastball and you expect a fastball, then I get -1 happiness points because you just hit a home run, and you get 1 happiness point because you just hit a home run. So -1, 1. And the same goes in the world where I threw a curveball and you were expecting a curveball. -1 happiness points for me, I look like an idiot. 1 happiness point for you, you look like the hero of the game. The situation is reversed if I throw a fastball and you were waiting for a curveball. If I throw fastball and you wait curveball, then I strike you out. And I get 1 happiness point for that, and you get -1 happiness points for that. My success is your failure, and my failure is your success. Similarly, down here, if I throw a curveball and you were waiting for a fastball, I strike you out. 1 happiness point for me, -1 happiness points for you. So in other words, you want to find us at the same place, fastball, fastball, or curveball, curveball, and I want to find us at different places. I want to keep you guessing it. Let's try to find all the pure strategy Nash equilibria of this game. And just for speed, I'll do this with best response. If I knew that you were waiting for a fastball, I could throw a fastball and get -1 happiness points and get sent back down to the minors, or I can get 1 happiness point for striking you out. If I throw a curveball, I strike you out and I look awesome. I win the Cy Young. If I knew that you were waiting for a fastball, I would throw a curveball. We don't need science for this. Similarly, if I knew that you were waiting for a curveball, I could throw a fastball, strike you out, Cy Young Award, 1 happiness point. Or I could throw a curveball, You hit a home run, I get sent back to the minors, out of baseball, -1 happiness points. I would rather throw a fastball. So if I knew you were waiting for a fastball, I'd throw a curveball. And if I knew that you were waiting for a curveball, I'd throw a fastball. Let's talk about you. You're a column player. So if you knew that I was going to be throwing a fastball, you could wait for fastball and get 1 happiness point, or wait for curveball and get -1 happiness points. Silver slugger, back to the minors. You'd rather get the silver slugger award, 1 happiness point. You would rather sit fastball. If I was throwing fastball, you'd wait for a fastball. And if I was throwing a curveball, you'd wait for a curveball. You could either wait for a fastball and get sent back down to the minors, or you could wait for a curveball and hit a home run and win the Silver Slugger Award. Isn't that hard? But notice something. There isn't a pure strategy profile where we both have a best response there, right? So fastball, best response for you, but not for me. Curveball, best response for you, but not for me. Curveball, fastball, best response for me, but not for you. Fastball, curveball, best response for me, but not for you. There does not exist a pure strategy Nash equilibrium in this game. There does not exist a pure strategy Nash equilibrium in this game. This game of anti-coordination has no mixed strategy Nash equilibrium, which means that the funding agency called, which apparently is going to be the society, the sabermetricians this time, I got nothing to tell them. I don't have anything to tell them. The funding agency called and I got no prediction. I got no ending to the story. As of right now, they're just going to be like cycling forever. Do a steady state analysis of this and you'll see what I mean. You'll see that we just sort of like keep circling around the game. We never find a gravity point. We never find a sinkhole. Does that mean that we can't do anything with this game? No. It means we have to use the mixed strategy approach we were talking about before. Okay? So, suppose that I was throwing a fastball with probability P and throwing a curveball with probability 1 minus P. And suppose that you were waiting for a fastball with probability Q and waiting for a curveball with probability 1 minus Q. Just like in the A block. Now, I can work out the expected utilities for each of these options as a function of the other person's lottery. So my expected utility, the pitcher's expected utility of throwing a fastball, well, with probability Q, we're at fastball, and I get -1 happiness points. And with probability 1 minus Q, we're at fastball curveball, and I get 1 happiness point. So that's -1 times Q plus 1 times 1 minus Q. You work that out, that's 1 minus 2Q. My expected utility of throwing a fastball is 1 minus 2Q. 1 minus 2Q. Notice that if Q is 0, if you're always waiting for a curveball, then my expected utility of a fastball is 1. And if Q is 1, so that you're always waiting for a fastball, then my expected utility of throwing a fastball is -1. It's better and better when Q is lower and lower. And my expected utility for throwing a curveball, well, with probability Q, you're waiting for a fastball. We're at curveball, fastball, and I get 1 happiness point. So Q times 1 plus, well, with probability 1 minus Q, you're waiting for a curveball. We're at curveball, which means that I get -1 happiness points. So it's Q times 1 plus 1 minus Q times -1, which is 2Q minus 1. 2Q minus 1. 2 times Q minus 1. Notice this time that if Q equals 1, so that I know that you're waiting for a fastball, then I get 2Q minus 1, which is 1. And if I know that Q is 0, so that you're always waiting for a curveball, then that's 2Q minus 1 is -1. So again, it just works out to, if you knew that you were playing a pure strategy, you'd wind up with one of the numbers that's already in the matrix. But the fact that Q can be intermediate, you might wait for fastball some of the time and curveball some of the time. That sets it up so that I can have intermediate expected utilities that aren't just 1 or -1. For example, notice that if Q equals 1/2, then my expected utility for both of these options is 0. Right? That's going to be substantively important. So please notice that if Q equals 1/2, then I don't care if I throw a fastball or curveball. I'm indifferent between the two things. Let's work out the expected utilities for you. Suppose that I'm throwing a fastball with probability P and throwing a curveball with probability 1 minus P. Then your expected utility of waiting for a fastball is P times 1 plus 1 minus P times -1, which is 2P minus 1. 2P minus 1. So the more likely I'm throwing a fastball, the happier you are. And the more likely I'm throwing a curveball, the less happy you are. Finally, if your expected utility of waiting for a curveball is p times -1 plus 1 minus p times 1, which is 1 minus 2p. So notice that we have the same sort of structure in our expected utilities, but the preferences are exactly reversed. I went 1 minus 2q and 2q minus 1, and you went 2p minus 1 and 1 minus 2p. Again, notice that if p equals 1/2, then you don't care, because if p equals 1/2, then your expected utility of waiting fastball is 0, and your expected utility of waiting curveball is 0. You'll notice also, if I draw a little picture for both of our players, so let me just put the opposing player's probability on this axis. Here's p equals 0, and here's p equals 1. All right? So if p equals 0 and p equals 1, then 2p minus 1 gets higher and higher as we get closer and closer. 2p minus 1 gets higher in p. If p equals 0, it's -1. If p equals 1, then it's 1. But I'm allowed to have all these intermediate things along this line. Conversely, 1 minus 2p gets worse and worse as we move to the right. So instead of going this way, like 2p minus 1, now it goes this way. We're at 1 over here, we're at -1 over here, and you'll notice that there's only one crossing between these two things. There's only one probability where these two expected utilities are equal, and that's when p equals 1/2. Why do I say this? Well, if you knew that one expected utility was higher than the other, then you'd play one option for sure. So if you knew that I was throwing fastball a lot of the time so that p was greater than 1/2, if p was greater than 1/2, if we find ourselves on this half of the plot, then your expected utility of waiting for a fastball is 2p minus 1, and your expected utility of waiting for a curveball is 1 minus 2p. So if p is 3/4 or 7/8 or something greater than 1/2, then you would rather wait for fastball than curveball, strictly so. Your expected utility for waiting fastball is strictly higher than your expected utility of waiting curveball. So your best response here is to wait fastball. If you think it's pretty often that I throw fastball, you should wait fastball. Conversely, if you think it's pretty likely that I'm going to throw a curveball so that p is pretty low, well, you can wait fastball and get 2p minus 1. If p is small, that's less than 0. Or you could wait for curveball and get 1 minus 2p, which, if p is small, is greater than 0. So if you think it's pretty unlikely that I'm going to throw a fastball, you should wait for a curveball. You should wait for curveball. Likely fastball, wait for fastball. Likely curveball, wait for curveball. That's what you're doing as a hitter. However, if I'm throwing a fastball exactly half of the time, if p equals 1/2, then you really don't care. You really don't care. You're indifferent. You're indifferent. And it no longer matters whether you wait for fastball, wait for curveball, or anything in between. You can wait for fastball half of the time, wait for curveball half of the time. You can wait for fastball 3/4 of the time and get 0 happiness points in that 3/4 of the time. Or you can wait for curveball 1/4 of the time and get 0 happiness points that 1/4 of the time and always wind up with the same 0. You don't care here. If p is less than 1/2, so that fastballs are unlikely and curveballs are likely, then you do best by setting q equals 0 and waiting for a curveball all the time. Your best response here is q equals 0. However, if fastballs are very likely, if p is greater than 1/2, then your best response is to set q equals to 1 and wait for fastball all the time. Right? And exactly at the point p equals 1/2, anything will do. Q could be any number. Q could be any number between 0 and 1. Just to encode this, I'll introduce the notion of player 2's best response correspondence, just like before. B sub 2 of p. It reads in my probability, that's sigma sub minus I, and it spits out what your best mixing probability is, what your best Q is. And most of the time, almost all the time, your best response is a pure strategy. 8-bit bad guy. But at exactly Q equals 1/2, you're indifferent and anything would do. Anything would do. Notice that that means that a necessary condition for mixing, the only time that you would ever mix, the only time that you would mix, the only time that you would choose a Q that wasn't 0 or 1, the only time that you would truly mix over your outcomes is if I chose a P that rendered you indifferent at P equals 1/2. You wouldn't mix here, you wouldn't mix here. You only mix when you're indifferent. I choose my P in a mixed strategy Nash equilibrium. I choose my mixing probability in a way that renders you indifferent. If you're mixing too, a necessary condition of you mixing is me choosing my P in a way that makes you indifferent over your outcomes that you're mixing over. There's a lot going on in this bow tie. This bow tie has a lot in it. But this is the way to see your best response. Let's think about this from my perspective. So you remember, my expected utility for throwing a fastball was 1 minus 2Q, right? If Q is high, then I do badly, and if Q is low, then I do well. So 1 minus 2Q and 2Q minus 1 for throwing a curveball. So let's have Q on this dimension, right? So at Q equals 0, then you're always waiting for curveballs. And at Q equals 1, you're always waiting for fastballs, okay? So my expected utility for throwing a fastball is 1 minus 2Q, which gets smaller and smaller as Q gets bigger and bigger. So at Q equals 0, throwing a fastball gets me 1 happiness point. And at Q equals 1, throwing a fastball gets me minus 1 happiness points, right? And so it just goes right down like this. Conversely, my expected utility for throwing a curveball is 2Q minus 1, which is getting higher and higher. If Q equals 0, so that you're always waiting curveball, then my expected utility of throwing a curveball is minus 1. And if Q equals 1, so that you're always waiting for a fastball, then my expected utility of throwing a curveball is 1. So it's the same shape, it's just that I don't want the same things that you want, but it's the same exact shape. In other words, if Q is smaller than 1/2, so that you're waiting curveball a lot of the time, then I should throw a fastball. I want to strike you out. If I think it's very unlikely that you're waiting for a fastball, I'll throw the fastball. And if I think it's likely that you're waiting for a fastball, I'll throw the curveball. And at Q equals 1/2, I don't care. Same bow tie, just different player, different option. 8-bit bad guy. So let's just think this through in terms of my best response then. So if Q is less than 1/2, then if you're waiting for fastball rarely, my best response is to throw a fastball by setting P equals to 1. And if Q is greater than 1/2, so that you're waiting fastball pretty often, my best response is to throw a curveball by setting P equal to 0. P equals 1, P equals 0. And if Q is exactly equal to 1/2, if you're waiting fastball half the time and waiting curveball half the time, then any P will do the same because I'll be indifferent between the two options. So if Q equals 1/2, any P will do. P equals 0 gets me 0. P equals 1 gets me 0. P equals 1/2 gets me 0. I don't care. A necessary condition of my mixing is that you choose just the right Q. Q equals 1/2. So what I want to do is I want to put this into a square. I want to put these best response correspondences into a square. Okay? I'm going to put my mixing probability here on the bottom axis. So over here, I'm never throwing a fastball and I'm always throwing a curveball. P equals 0. And over here, I'm always throwing a fastball and never throwing a curveball. P equals 1. P equals 0, P equals 1, P equals 1/2. Oh, right at the heart. And I'll put your mixing probability on this axis. So Q equals 0, you're always waiting for a curveball, you're never waiting for a fastball. Q equals 1, you're always waiting for a fastball, never waiting for a curveball. Notice that the 4 corners of the square are the 4 pure strategies, right? So down here, this is P equals 0 and Q equals 0. This is curveball, curveball. And this is fastball, fastball. You're happy here and you're happy here, and I'm sad here and here. Down here at the bottom right, that's fastball, curveball, right? So P equals 1 and Q equals 0. Now I'm happy and you're sad. And over here, this is P equals 0 and Q equals 1. That means that I'm never throwing a fastball and you're always waiting for one, so I'm happy. So what I want to do here is I want to plot these best response correspondences in this space. So I'll mark the 1/2 on my axis and the 1/2 on yours. And let's work through my best response correspondence first. So let's suppose that it's unlikely that you're waiting for fastball. Let's suppose that Q is less than 1/2. Q is strictly less than 1/2. So if Q is strictly less than 1/2, then I want to throw a fastball for sure. I want to throw a fastball for sure. So I'm going to draw a line right up this edge of this square. Now, if Q is high instead, then what I want to do, if I think it's very likely that you're waiting for fastball, I want to throw a curveball by setting P low. So P low if Q is high, P high if Q is low. I want to strike you out. However, right in the middle, if Q equals 1/2, I don't care, and any P will do. Any P would do if Q equals 1/2. So in other words, my best response goes down, over, and then down again. If I think you're waiting for curveball, I throw fastball. If I think you're waiting for fastball, I throw curveball. And if I think you're mixing 50-50, I don't really care. Any mix would give me 0 happiness points. As for you, suppose that you think that it's unlikely I'm going to throw a fastball. If you think P is low, then you're going to set Q low, and we can just ride right down along this edge of the square. Similarly over here, if you think it's very likely that I'm going to throw a fastball, you're going to wait for a fastball. So fastball unlikely, don't wait for fastball, pure strategy. Fastball likely, wait for fastball, pure strategy. If the fastball is a 50-50 proposition, then a 50-50 proposition for you would do, as would anything else. You can mix there. So you're allowed to mix when P equals 1/2. I'm allowed to mix when Q equals 1/2. You'll notice that we don't have any pure strategy Nash equilibria because there isn't a corner where we're both best responding. So down here at bottom left, you're happy and I'm sad, right? You're best responding and I'm not, because I'm throwing a curveball and you're waiting for it. Up here, I'm throwing a fastball and you're waiting for it. So you're best responding and I'm not. And up at these corners, I'm best responding and you're not. I'm either throwing a fastball when you're not waiting for it, or I'm throwing a curveball when you're not waiting for it. The only time that these things all mix is exactly in the middle at 1/2, 1/2. P equals 1/2, and therefore 1 minus P equals 1/2. Q equals 1/2, and therefore 1 minus Q equals 1/2. That's a mutual best response. My P is a best response to your Q, is the best response to my P, is the best response to my Q,
is the best response to my P, is the best response to your Q, is the best response to my P, is the best response to your Q, is the best response to my P, is the best response to your Q, is the best response to my P, is the best response to your Q, is the best response to my P, is the best response to your Q, is the best response to my P, is the best response to your Q, is the best response to my P, is the best response to your Q, is the best response to my P, is the best response to your Q, is the best response to my P, is the best response to your Q, is the best response to my P, is the best response to your Q, is the best response to my P, is the best response to your Q, is the best response to my P, is the best response to your Q, is the best response to my P, is the best response to your Q, is the best response to my P, is the best response to your Q, is the best response to my P, is the best response to your Q, is the best response to my P, is the best response to your Q, is the best response to my P, is the best response to your Q, is the best response to my
equilibrium. This is a mixed strategy Nash equilibrium, or just Nash equilibrium. This game has a prediction, but it just isn't on the corners. This game has a prediction, but it's not in pure strategies. I'm not playing a pure strategy of curveball. I'm not playing a pure strategy of fastball. You're not playing a pure strategy of fastball. You're not playing a pure strategy of curveball. There isn't a best response along the edges. There isn't a best response along the corners. The only best response is in the middle of the square. That's mutual best response. That's equilibrium. That's a mixed strategy Nash equilibrium. We can show up to the funding agency and have something. We're not going to show up empty-handed. Right? That's good news. So let me give you a theorem. Consider any game that has a finite number of players and where every player has a finite set of actions. So N has a finite number of elements in it, and each A sub I has a finite number of elements in it. Then that game has at least one Nash equilibrium in pure or mixed strategies, or just Nash equilibrium. This is called Nash's theorem. Nash's theorem means that if you have a finite number of players, each equipped with a finite number of actions, could be huge, which is a voice crack thing, could be huge but finite, could be a Google Things. So long as it's a finite number of players and a finite number of actions for every player, you'll have at least one equilibrium. Now you might have multiple, but you'll have at least one. You'll never not make a prediction. Our enterprise is well posed. That's what this means. How would you show something like that? Actually, Nash's theorem the proof of it is more clever than it is ingenious, right? It's a really short proof. It's 2 pages. This was in John Nash's dissertation, which was 28 pages total, and wound up winning a Nobel Prize in economics. 2-page proof. Actually, when a young John Nash, as he was finishing his dissertation at Princeton, told a more mature John von Neumann, who was at the Institute for Advanced Study at Princeton. So Nash tells von Neumann, the inventor of game theory, basically, about this, and von Neumann said, "Oh, that's trivial. That's just a fixed point theorem. Oh, it's trivial. It won a Nobel Prize, but it's trivial." So that's a mixed strategy Nash equilibrium. You can rest assured, and I know that this was bothering you, if you write down a game that has a finite number of players and a finite number of actions, there's always at least one prediction. But it might be a little bit trickier to think your way through. It's not the same as straight. It's not the same thing as swerve. Now you have to say, well, they'll throw a fastball some of the time and a curveball some of the time. And the way that we specified the utilities, it turns out 1/2, 1/2. Notice that we had changed the utility numbers a little bit. Now the scale matters. Why? Because it'll change the mixing probabilities of our prediction. You'll see what I mean on the problem set. You have that to look forward to. But at minimum, now you know Nash's theorem, which is one of the most foundational, if not the most foundational result in game theory. It's the thing that lets us proceed. Without knowing that, then we could program a computer to try to find the solution to some gigantic system of equations, even though it didn't have a solution. That's bad. You'd never learn. You'd never find that out. It would just keep running forever until you gave up hope. But even then, you wouldn't know. Is there some solution out there? Nash's theorem lets you know your enterprise is well posed. Our enterprise is well posed. We can keep telling each other stories without any fear about not knowing how they end. So over in the C block, I want to do one more example by talking about chicken, which has pure strategy Nash equilibria, but also a mixed one. Can't wait to show you that. See you there. So here in the C block, I just want to do some more mixing. And in particular, let's mix chicken. I don't even know what that means. So here are the game of chicken again. I know you're tired of it by now, but it's so awesome. So remember, I'm an angst-ridden adolescent. You're an angst-ridden adolescent. We are two angst-ridden adolescents. And we're trying to show who's more awesome. And we're doing this by driving toward one that are very high speeds or toward a cliff or you know, I'm putting weapons in Cuba and you're putting weapons in Western Europe or Turkey. Who knows? So remember, I can swerve or I can go straight. And you can swerve or you can go straight. Swerve, swerve. It's a tie, 1 happiness point apiece. Swerve straight, you win. I look like a chicken. 0 happiness points for me, 2 happiness points for you. Straight swerve, situation reversed. 2 for me, 0 for you. Straight, straight, we drive into one another, fiery car crash. -1, -1. So you'll remember that this game has 2 pure strategy Nash equilibria. There's the one where I go straight and you swerve, and the one where I swerve and you go straight. Right? There's winners and there's losers in our pure strategy analysis of chicken. Even though we already have some predictions, I'd like to try to understand the game all the way. And in order to do so, I want to evaluate whether or not it has any mixed strategy Nash equilibria. To do so, let me just write out the expected utilities for each of the alternatives on the assumption of some mixing. So suppose that I swerve with probability P, and therefore go straight with probability 1 minus P, and similarly for you with Q and 1 minus Q. Now, my expected utility, role player's expected utility for swerving. Well, with probability Q, we're at swerve, swerve, and I get 1 happiness point. And with probability 1 minus Q, we're at swerve straight, and I get 0 happiness points. So Q times 1 plus 1 minus Q times 0 is just Q. My expected utility, if I swerve, is Q. My expected utility for going straight, however, well, with probability Q, we're at straight swerve, and I get 2 happiness points. So 2 times Q, plus with probability 1 minus Q, we're at swerve, swerve, we're at straight, straight. So -1 times 1 minus Q. You work that all out, you wind up with the expected utility of going straight is 3Q minus 1. Notice that means that the indifference point, the Q that renders me indifferent, is again Q equals 1/2. If Q equals 1/2, then Q is 1/2. And 3Q minus 1 is 1/2. 3 halves minus 1 is 1/2. Therefore, 1/2 is when I'm indifferent. So if Q is low, if you're not swerving very often, then I want to swerve. If Q is a small number, then Q is strictly greater than 3Q minus 1. So in other words, if Q is strictly less than 1/2, I want to set P equals to 1. I want to swerve. And if Q is high, if Q is strictly greater than 1/2, then I want to go straight. I want to set P equals to 0. And if Q is exactly equal to 1/2, then I'm indifferent. The same argument goes for you. So let's say that I'm swerving with probability P and I'm going straight with probability 1 minus P. Well, then your expected utility of swerving is P times 1 plus 1 minus P times 0 is just P. And your expected utility of going straight is P times 2, 2P, plus 1 minus P times -1, which is 3P minus 1. And you're exactly indifferent when P is exactly equal to 1/2. If P is high, you'd rather set Q all the way down to 0. And if P is low, you'd rather set Q all the way up to 1. If it's unlikely that I'm going straight, then you want to go straight. And if it's unlikely that I'm swerving, then you want to swerve. So let's try to put this into a square again. So we'll put my mixing probability P here, and we'll put your mixing probability Q here. Here's P equals 0, here's P equals 1. I never swerve, I always go straight. I never straight, I always go swerve. And likewise for you. If Q equals 0, you never swerve, you always go straight. If Q equals 1, you never straight, you always go swerve. And I'll mark the 1/2 again. Notice that this time we do have two pure strategy Nash equilibria. So there's one pure strategy Nash equilibrium where I'm swerving and you're going straight. And there's another pure strategy Nash equilibrium where I'm going straight and you're swerving. Okay? So we should expect to see some intersections of the best response correspondences at these corners. All right? Let's see if that works out. So let's plot my best response first. So if I know that it's unlikely that you're going to swerve, then I want to swerve for sure by setting P equals to 1. And if I know it's likely you're going to swerve, then I want to go straight by setting P equals to 0. Not swerving, going straight. So here are my best responses this time, and we've got this line right through the middle. If Q equals 1/2, then I don't care. Any P would do. I'm indifferent. What about you? You're column player. So in this situation, if you know that P is low, so that it's unlikely that I'm swerving, then you want to swerve. So you're going to be up here. You want to set Q equals to 1. And if you know that it's likely that I'm going to swerve, then you don't want to swerve. You want to set Q equals to 0. And then there's this line right through the middle where if I'm going straight with probability 1/2 and swerving with probability 1/2, you don't care. You're indifferent. You'll notice that we do indeed have these two intersections we were hoping for. The one where I always swerve and you don't, and the one where you always swerve and I don't. However, you'll notice also that exactly 1/2, there's another equilibrium in mixed strategies where I go straight half of the time and swerve half of the time, and you go straight half of the time and swerve half of the time. I'm like this, you're like this. Notice this time that there's like a little bit more, we're kind of working together. And that's why we have these two corners. That's why we have these two corner equilibria. This is the one where I always swerve and you always go straight. And this is the one where I always go straight and you always swerve. But this extra equilibrium, this third equilibrium, is one where we're both mixing it up. I should note while we're here that for reasons that are actually kind of related to this picture in a more elaborate sense, here's a result that will help you when computing Nash equilibria. For almost all games, where I mean this in a very strict sense, for any game that I show you, almost all games that you could write down, if you drew a game at random, the probability of the following result will be 1. It is almost always the case that the number of Nash equilibria total is odd. It could be 1, like in baseball, it could be 3, like in chicken. But it is incredibly unlikely that you'll ever have an even or an infinite number of equilibria. Almost all games have a finite and odd number of equilibria. That's useful because it means that if you get to two pure strategies, you should go looking for a mixed one. That is what in chicken, that's what just happened. We had two pure strategy Nash equilibria, and we went looking for a third one, and lo and behold, there it was. Now let's think this through from a normative standpoint. Let's do some welfare analysis. The first thing I want to do is put row players' utilities here and column players' utilities here. Now notice that I've got 4 outcomes and pure strategies to plot in this space. It could be that we both swerve, which gets us to 1-1. It could be that I win and you lose. It could be 2-0, right? So that means go further this way and down. 2-0 is right here, and 0-2 is here, right? So this is I win and you lose. This is you win and I lose. This is the tie. And then, of course, there's the fiery car crash, which is down here. -1, -1. So notice that we've got two pure strategy Nash equilibria, and I can just see them in this utility imputation space. In one of them, I'm winning and you're losing. 2 happiness points for me and 0 for you. And the other one, you're winning and I'm losing. 0 happiness points for me and 2 for you. So losing is better for both the winner and the loser than dying. Notice also that the tie is a Pareto improvement over -1, -1, but there are no other Pareto arguments. There's a Pareto frontier. There's a Pareto frontier that goes from the one where I'm happy over to the one where we're both kind of happy, over to the one where you're happy and I'm sad, right? So this is our Pareto frontier. And what I want to do is I want to figure out what the expected utilities for our new mixed strategy Nash equilibrium are. What are the expected utilities? So let's go back to our game and notice with me that each of the 4 cells in the game, each of the 4 possible outcomes happens with probability 1/4. 1/4 of the time there's a tie. P times Q, 1/2 times 1/2 is 1/4. And so we find ourselves in this cell 1/4 of the time. P times 1 minus Q, 1/2 times 1/2. We find ourselves in this cell 1/4 of the time. We find ourselves in this cell, straight swerve, 1/4 of the time. And we find ourselves in the fiery car crash 1/4 of the time. Let's think through my expected utility given what we just figured out. So this equilibrium yields 1/4, 1/4, 1/4, 1/4, which means that my expected utility is 1/4 times 1 for swerve, plus 1/4 times 0 for swerve straight, plus 1/4 times 2 for straight swerve, plus 1/4 times -1 for straight. That works out to 1/2. My expected utility in this equilibrium is 1/2. I win 1/4 of the time, which is great. I tie 1/4 of the time, and I lose, and I die 1/4 of the time. When I lose, it's 0 happiness points. And the same goes for you. If you work it out, your expected utility for this is also 1/2. So if I go back to the utility imputation space, you'll notice that the third equilibrium in expectation generates a utility imputation of 1/2, 1/2. 1/2, 1/2, which is Pareto dominated by 1/1. So the tie outcome, swerve, Pareto dominates this mixed equilibrium. However, neither of the pure strategy Nash equilibria do. So neither 0-2 nor 2-0, Pareto dominates 1/2, 1/2, because whoever is getting the 1/2, whoever the loser is in a pure strategy Nash equilibrium, prefers this mixed equilibrium to losing for sure. 1/2 is better than 0. This introduces a difficult question. How do you compare waste and fairness? Why do I say that? Well, you'll notice that we've got 2 pure strategy Nash equilibria that are Pareto efficient but unequal. There's a winner and a loser. 2-0, 0-2. And you'll notice we've got a third equilibrium, 1/2, 1/2, which is egalitarian but wasteful. Why is it wasteful? It's wasteful because we introduced the possibility of a car crash. However, because of the tension involved in the game, that introduction of waste ends up generating an egalitarian outcome. So you can either have a winner and a loser in pure strategies and create Pareto efficiency because there are no crashes. Or you can introduce the chance for a crash, wind up with an egalitarian outcome, and have to endure the waste. There isn't a right answer to this. It kind of depends on how severe the car crash is. If it's genuine car crashes, I prefer winners and losers. If it's nuclear war, I prefer winners and losers. If there's other situations, it's not that hard to imagine preferring the egalitarian outcome if it isn't too wasteful. The worse the -1 is, the more wasteful this all becomes, and therefore the stronger this argument is in favor of the winners and the losers. The better the -1 is, the better the wasteful outcome is, the worse the argument for winners and losers is because you're not that far from the Pareto frontier and you just got a lot of egalitarianism. The waste and fairness argument helps us to understand how many car crashes we're willing to endure in the name of generating a more equal outcome relative to the winners and losers. And I'm telling you, there isn't a right answer to that. You have to become an introspective analyst. You have to think through how bad is a car crash in a given situation? How wasteful is the waste? You have to think through how awesome is the winning and the losing? How unequal is the unequal? And you have to weigh the wastefulness of the waste against the unequalness of the inequality. And once you've weighed those out, then maybe you have a better chance of understanding which of these penny situations you prefer. But that all happens only if you're an introspective analyst. All of that from Chicken. There's a reason it's one of my favorite games. Chicken highlights a lot of important tensions, not just about who's going to win and who's going to lose, brinkmanship, but also how do we weigh these competing normative interests that pop up so often in this class. So I hope that this is something that resonates with you because I think that it's a very stark characterization of an important point. You have to endure waste And that sounds childish when I'm talking about pennies with me and Chewy. When I'm talking about car crashes or nuclear wars. When I'm talking about genuine backing down in political situations with high stakes. When I'm talking about very wasteful waste and very unequal inequality. There isn't a right way to balance it, and you have no choice but to reflect. And I hope that you do that pretty often. So what are we talking about today? I mean, it's a technical lecture. There's no getting around it. No matter how hard I work at waste and fairness in baseball, oh yeah, baseball's so substantive. No matter how hard I work at it, today's lecture is a technical lecture. This is one of those things you have to slog through to be able to say, yeah, I know what game theory is kind of about. If you want to use the tool of Nash equilibrium, as any graduate of a class like this should be able to do, then you have to know when it works and when it doesn't. However, we also saw that there's some really interesting substantive wrinkles that can emerge with mixed strategies when we're mixing over something that might be wasteful. If mixing introduces a potential for waste that's quantified through the endogenous mixing probability, the optimized strategic randomization, if I introduce a mixed strategy Nash equilibrium where sometimes I do a wasteful thing, or sometimes we do a wasteful thing together, that introduces all sorts of interesting substantive wrinkles because it means that there might be clean answers that do well on one normative criterion but not the other, and messy answers that do well on some other normative criterion but not the first. That's a nice substantive punchline for us to end it with, but let's just be honest, this was a tough technical lecture. So you might be thinking to yourself that this mixing probability is this weird esoteric thing that's a saving grace for those of us that want to be analysts. And you're kind of right about that. Mixed strategy Nash equilibrium is hard to understand. It's hard to intuit because we play this game one time, and it's unlikely that somebody is out there rolling a d20 or something so that they can generate just the right probability, randomize at just the right rate, to do this optimized strategic randomization so that this one slice of this other slice, so that we can get these little random slices of a square to intersect with one another. That seems very esoteric and doesn't seem like how baseball players really play. They get to repeat the interaction several times, and so probabilities make sense. But brinkmanship games, or situations where there's a genuine car crash, that might only be played one time, and so these probabilities don't make any sense. Strategically optimized randomization doesn't make any sense in some cases. If it's a truly one-shot interaction, then why are we talking about probabilities when it's unlikely that most players actually randomize that way? And it's with your very understandable doubtfulness in mind that I'd like to conclude with a provocative thought. Consider the game of rock, paper, scissors. So it's a child's game that oftentimes is used to make decisions. And the idea is we're going to go 1, 2, 3, and then put out a hand gesture at the same time. Not a bad hand gesture. The hand gesture is going to be one of three things. I can throw out a rock hand gesture, I can throw out a paper hand gesture, or I can throw out a scissors hand gesture. And the idea is that which one beats which depends on a substantive story that makes sense. If we throw out the same hand gesture, if I throw out rock and you throw out rock, it's a tie. Scissor, scissor, tie. Paper, paper, tie. However, if I throw out rock and you throw out scissors, then I win because my rock beats your scissors. That actually kind of hurt. And if I throw out scissors and you throw out paper, then I win because scissors cuts paper. Just imagine, just all sorts of carnage. Put on a chainsaw. And for reasons that nobody fully understands, if I throw out paper and you throw out rock, then the paper envelops the rock and paper beats rock. So rock beats scissors, scissors beats paper, paper beats rock. It's sort of circular. I would encourage you to work this out yourself to learn that game has zero pure strategy Nash equilibria. There isn't a steady state. If you knew I was throwing out rock, you throw out paper for sure, and rock isn't a best response to that. If you knew I was throwing out paper, you throw out scissors for sure, and paper isn't the best response to that. If you knew that I was throwing out scissors, you throw out rock for sure, and scissors isn't the best response to that. There is not a pure strategy Nash equilibrium. There's a mixed strategy Nash equilibrium where we each play them a third of the time. Now, let's say that you and I were going to play rock, paper, scissors together one and only one time. It's a one-shot interaction. You may know in your head that you're going to throw out rock for sure. You might know that. You might know you're going to throw out rock for sure, but I don't. I can only assign subjective probabilities to that. Now, I could throw out whatever probabilities I wanted to, but to be completely honest, I would go into this thinking a third, a third, a third. a third rock, a third paper, a third scissors. And I'm assuming that even though I know for sure what I'm going to play, you don't get to know that, and you're probably thinking that I'm working this through probabilistically myself. The only way that this makes sense, in a sense, is for us to know what we're doing for sure, but for there to be something that you don't know about me, namely what's going on in my mind, and similarly with me for you. So even if there isn't any randomization going on once we've made up our mind, there's still some randomization going on. It's just sort of more of a fable randomization, where even if I know what I'm doing for sure, you have a fable of me that doesn't. Now, in order for equilibrium to truly explain things, it has to be the case that I wouldn't always put out rock or paper or scissors if there were tens of thousands of this interaction, of a one-shot interaction. Millions, billions, trillions, many versions of us playing rock, paper, scissors. A classical interpretation of probability would be, even if we're playing this game one and only one time, there's a large number of possible us's. And in 1/3 of those, I'm playing rock. In 1/3 of those, I'm playing paper. And in 1/3 of those, I'm playing scissors. So in order for this to work out, that would have to be the case, even though we're playing one and only one time. Alternatively, I might roll a 3-sided die that says rock sometimes, paper sometimes, and scissors sometimes. I could truly randomize as in the story. Those would give us 2 equivalent landing points for this fable of rock, paper, scissors. So randomization can happen because of actual randomization, or randomization can happen because of this very fictitious randomization in your opponent's head. So we could try to torture the interpretation of our mixed strategy Nash equilibrium analysis to make it fit, either by having people who are implausibly contemplative and competent by rolling D3s, or implausibly infinite like parallel versions of ourselves. Either of those is slightly tortured, but gets us to where we need to go for this story to make any sense. And so you might be thinking, well, we could torture the story one way or torture the other, but either way, we're torturing it. And that makes sense. But there's a third way that we could torture it that makes a little bit more sense than our first 2 tortures. The third is going to require what we talk about in a few weeks, but I can introduce it now. It could be that we don't have an uncertainty about what each other is doing. It could be that we're playing pure strategies. You're not uncertain about me, and I'm not uncertain about you. But we are uncertain about which game we're playing. Maybe you know just for sure how much you enjoy winning with rock. And you know for sure how much you enjoy winning with scissors. And there's some slight differences between winning with rock, winning with paper, winning with scissors, losing with rock, etc. There's some small perturbations in your utilities that you know about and I don't. And there's some small perturbations in my utilities that I know about and you don't. I just love winning with scissors because it's just more carnage. And you don't quite know if we're playing a game where I love winning with scissors or don't like winning with scissors. There's uncertainty not about what I'm doing, but about which me I am. And there's uncertainty not about what you're doing, you're playing a pure strategy, but there's uncertainty about which you are. Are you the one that likes to win with rock? Are you the one that likes to win with paper? Are you the one that likes to win with scissors? There's a little bit of uncertainty, not about what the players are doing, but which type of player they are. And so what happens is, for any mixed strategy Nash equilibrium in games like we talked about, where everybody knows the game, but they don't know what the other player is doing necessarily, there exists a pure strategy Nash equilibrium in the world where we don't quite know which game we're playing. So uncertainty about what we're doing might be implausible, but it's also just a stand-in for uncertainty about the opponent, which is plausible. You don't know everything about the opponent, even if you know exactly what they're doing. In other words, I could have uncertainty about what you're doing, or which you are, or both. And you could have uncertainty about what I'm doing, or which me I am, or both. There are multiple ways for us to microfound uncertainty. And each of these ways to microfound uncertainty adds another layer to our von Neumann and Morgenstern style analysis, which in turn leads to different variants of our Nash equilibrium analysis. The mountain that we've been climbing up has been one unified slope. A lot of this is more connected than you might have been able to appreciate as we were going through it week by week. There are deep connections between uncertainty, and thus von Neumann and Morgenstern, strategic randomization, and thus Nash, and what we will soon see is incomplete information, things that I know about myself that you don't, or things that you know about yourself that I don't. If we want to be patient, if we want to keep walking down the trail, even though sometimes it confuses us, if we're willing to just wait and see what's waiting ahead of us, even if some of the time we say, well, this doesn't seem to quite make sense. If we're just patient, then we can find new ways to torture our games that make a little bit more sense than some of the other previous torturous ways to handle our games. Right? So there's oftentimes a simple, straightforward interpretation of something, and then a key connection between that simple, painfully, stupefyingly simple version of something that doesn't seem plausible, and then some slightly richer model that just requires some more apparatus. We're not done. We've only ended the first section of game theory. This is the end of the beginning of our game theoretic analysis. We know what rationality is. We know what rationality under uncertainty is. We know what Pareto is. We know what games are and how to study them, both in pure and mixed strategies. And this end of the beginning might be something that makes sense to you in some regards and doesn't make sense to you in other regards. Now, I'm not going to be able to come up with an explanation for everything that doesn't make sense to you because this theory is not perfect. Rational choice theory is not perfect. Game theory is not perfect. There are genuine problems in interpretation. However, when we get to the next chapters, as we move past the end of the beginning and move on to some more advanced topics within game theory, I hope that you will take the time to say, wait a second, I see how this works based on this simple apparatus I've been taught. There's always more. There's always another wall to run through. The question is, do you feel the motivation to keep doing it? Do you feel the motivation to keep running through walls? Because some of those walls, the things that you see when you run past them, they might not totally make sense to you. Like mixed strategy Nash equilibrium. It's like, wait a second, that doesn't all the way make sense. And that's good. It makes you get critical. It makes you think through why we're going through all of this. And it makes you have humility about when it's an appropriate tool to understand a political phenomenon that you care about. However, it's not a good reason to stop running through walls. You should keep running through walls because it's fun to do so. You should keep running through walls because it's important that you never stop. You should keep running through walls because what's on the other side of the next wall might help to explain why you're so confused about what's on the side of this one. Your understanding continues to expand, but that doesn't mean that any given moment you have a complete characterization of the newest level. This end of the beginning might not be fully satisfying, and it's never going to be fully satisfying, but it might be more satisfying if you just keep running. So, let's keep running through walls together. Let's keep doing these stupid problem sets. Let's keep making these stupid movies, because the next wall might be the one that makes some of the previous walls make sense. Or it might not. In which case, all you've done is run through walls and gotten stronger, and hopefully you'll be ready for the next set of walls in some other substantive area of interest that you care about. And then you don't have to worry about me all the time, which is good because I'm sure I'm pretty annoying to you by now. I'm annoying to myself by now, 50 movies in. One thing I know is going to annoy you, however, is your problem set for the week. And I hope that it's annoyance that you can smirk about a little bit. So let's struggle, let's ask questions, let's keep pushing, let's run through more walls. But in the meantime, thanks for watching.